I was invited to this talk as a 5 o'clock tea seminar to talk about some AI updates. What are we doing in the field of AI? Of course, applied to remote sense and image processing or other fields. So thank you very much again for your invitation, and I'm so much honored. Actually, I didn't want to make this so boring lecture hour like something. I didn't want to lecture you. It's Saturday, it's coffee hour or tea hour, whatever you want. And I wanted to talk a little bit about rendering some talks. We've done everything almost in the field of AI right now. We tried deep learning and reinforcement learning, supervised, unsupervised, classification, segmentation, semantic segmentation, and all kind of stuff. So all the time we tried them in different applications. And what is it going to be, where is it going to be going for the next step? What should we expect? I mean, in all fields so far, we've seen that we see a hype. A lot of researchers are publishing a lot, but at some point we see that the publications are coming to a stage because there's maybe nothing new to do, or we are just feeling like maybe something new must come. And in my point of view, I feel like AI cannot become more intelligent in the way that we use it right now. So I will try to introduce some ideas of mine. Maybe they are not very realistic. Maybe some of them are realistic, some of them are not. My own thoughts about how to make AI really intelligent and how to go to the next stage, where to go from here. So here's if I can go to the next slide, yeah. And here is a layout of my small blah blah. I will give you a pinch of my own background, just you know my experience and what I worked on, what my interest is. And I will give you a tiny little bit taste from some AI applications that I've done here and there. So you can get a little bit taste. I'm sure all these methods that I used are being used by you, your students. You're also aware of them. So I don't want to bore you a lot with them. Then I want to go to the final step where I want to talk, render some thoughts with you. What I see as the future of AI, or where should we go to go forward. Oh, my slide a little bit is strange. Oh, okay, yeah, it looks a little bit strange. Okay, I'm sorry. So here you see in the map the areas that I've given lectures, and the green area, green star that you see is where my home is. That's my home place. And another tiny little star you see on Sweden, because I have to teach there. You know, I'm from Jönköping University, Jönköping AI Lab. I started to work there last January. And my background is computer vision, and I used machine learning, artificial intelligence methods a lot. And I got my PhD officially from Istanbul. And after my PhD, or just before my PhD, actually, I started to work in Germany. And I worked for a while in Germany, and during my living period in Germany, I also pursued habilitation study at University of Osnabrück. And some years after, I moved to the Netherlands. And since then, I'm, yeah, that's my home. And during my PhD, that's my interest. As you see, I was very much interested on how humans see and understand. I put this tweetie because I want to tell you a story about how I became so much interested in analyzing images. For instance, this tweetie, cartoon, children like it a lot, small kids. If you put tweetie, they laugh, they follow the picture, they really pay attention and find it entertaining. And at some point when the technology computer software became a little bit more available, they made this tweetie in 3D. They rendered the cartoon in 3D. They made more shadows and they made tweetie a little bit more realistic. And when they put this more realistic tweetie, they expected that children will like it more. But actually it didn't work because children didn't like it when they made it more realistic. The reason is that the kids couldn't understand that it's still tweety, and they didn't find it interesting at all. And that took my attention because I learned that in human vision system, in human eyes, there are some cells which are very sensitive to some edges and corners. So these are, when you do image processing, these are done mathematically with local filters. We design local filters. So these local filters are in our eyes, in our vision system. And when we are child, these sensitive cells are very much premature. They are not very much developed yet, and they can see only really very sharp edges, really very sharp corners. And if you put something very smooth shape, 3D rendered with shadows, the children's system cannot see those sharp edges anymore, cannot find it, and they cannot track it anymore. And this is developed afterwards. And when I was doing my PhD, I worked on extracting local features inspired from how humans sees. For instance, if I want to recognize this tweetie, if I was a child, how I should recognize it, I would look for some curves, some close shape, and some significant blue circles, and make some rules. So these rules are the computer vision algorithms that we worked on to recognize objects. And these are totally inspired from how children see. And later on, when we had AI algorithms, we started to give those images just directly from neural networks, and we said, extract features yourself and figure out what to look at here. But before AI, we were feature engineering with hand. We were putting those rules, what to look at, what features to extract, and what kind of rules to make to recognize a specific object. So that was my point of attention during my PhD, understanding how the human nervous system, the vision system is working, how the eyes are capturing the light, what kind of edge and corner responses are given to the brain, and when signals are in the brain, how do we make rules to say what object this is. So I worked on object detection algorithms, which are mostly rule-based, or we say we make these rules with probabilistic theory, for instance, in mathematics. And of course, these days, those rules, we don't want to engineer by hand. We want AI to find the optimal rule by itself instead of hand tailoring the algorithm. And we are expecting AI to do better than this because we show so many examples to look at what is the best rule is and to optimize the rule in the best way. So this is my major interest still, how human brain thinks, understand, and can I make machine see and understand. And a long time during my PhD and after my PhD, I worked with remote sensing data a lot. And I find it difficult to select one specific example to give because I worked on extracting roads, making road network automatically. I looked at environment, I extracted trees, and when I extracted trees, you see a 3D city of Delft here. This is TU Delft University of Technology, and its area in 3D in the figure. And we constructed those maps from remote sensing data. And I'm personally so much interested to make these algorithms fully automated, so less human power is necessary, because these images need to be really so big, or these 3D models needs to be really so big. And it's not feasible to do everything with human energy. It's not to replace human jobs, by the way, it's only to support human jobs. That's something important. I looked for making 3D buildings. And when I was looking at buildings, I worked with damage recognition. I looked at areas where earthquakes happened, and to understand the damage, doing some damage assessment in the area. I said when I looked at trees, I looked at the breast height diameter of the tree to say how much volume of carbon that tree can recycle. By looking at the breast height diameter of a tree, it's possible to estimate the volume of the tree and to say how much CO2 can be circulated through this volume of tree. And it's also possible to estimate how many trees are necessary by to this city, for instance, to keep it safe for human, to have a good air in this area. It's also possible to make such calculations. I, of course, looked at agriculture and looked at vegetation health, and to understand also soil moisture levels from satellite images. So you're experts in this field, and I don't have so much to tell to a group like you. You actually know more than I do, because I worked with satellite images a lot, but it's not my main area. So my main area is to develop algorithms which can see like human, understand images like human. And I also applied my background in my past 2-3 years to medical area. So you can also think that it's sort of remote sensing, because you are not really sensing touch to the object. But I was so much interested to make simple devices which can see, for instance, human skin, and can guide people to make decision maybe before going to the doctor, and track things at home by looking at skin directly. I will give you some pieces from my latest research in this area, and please think of those theoretical things that I mentioned here, how you can apply to remote sensing images, or if you apply to remote sensing images, maybe we discuss them later after this talk. I worked on how to recognize cancer on skin by using, for instance, simple cameras that people can track their state of cancer and to see if it's developing in a bad way or not, and to automatize this process and to make things robust. if you want me to mention, please later ask me to explain this. But I also don't want you to be really bored, because I'm expecting some of or most of the researchers who are attending to this webinar are very much aware of the theory, for instance, using a unit for semantic segmentation of a specific area that you see on the skin. So unit is trained to segment out the area automatically, and after segmenting out the area, we want to say how severe is the situation. Is it really level 1, level 2, level 3, 4, or 5 of the cancer? So of course this is officially determined by getting biopsy, because people, I mean doctors need to say the depth of the cancer. We cannot tell really from looking at the outside. They need to get biopsy to tell the exact level. However, if you ask to doctor, can you tell me the level by just looking, they say yes. Even before getting biopsy, doctors can tell you exactly the level that the person has without any biopsy. They just look from outside and tell it. So that again took my interest, because if you are able to just look and tell, that's also means that I can program something. A machine, algorithm can look and tell like you do. I talked to many doctors and I asked them, what are you looking at? I want to know, what are you looking at? Just like in Tweety, you are looking at edge, you are looking at blue eyes. Here, what are you looking at? Tell me, so I can program it like to see it like you see. And many doctors answered the same thing. They said intuition. So if you developed an intuition, you've seen a lot of examples, but you've seen some features there, right? What are those features where your intuition is developed? They found it very difficult to say. They couldn't really explain. But after asking more and more and more, maybe after 1 year, I found out that maybe somebody in medical field would reach the results faster than but I wasn't a medical expert. So for me, it took almost 1 year to figure it out how they determine. I found out that they look at the skin, and they look at this ABCDE features. Here, ABCDE stand for asymmetry, border irregularity, color fluctuation within the area, diameter of the area, and evolution, how quickly it's growing. So by looking at these 5 features, their intuition was developed. And then I had an aha moment. So if I understand how human is thinking, it's my aha moment, because I can program it. What you see, I can program. What I can program, I can make mathematical algorithms, of course, for asymmetry. I can use some PCA and look at the proportion between the major and minor axis and things like that to say the asymmetry. For border irregularity, I can open the border and see the fluctuation in the border. Again, for color fluctuation, I can extract some color invariant and see the standard deviation, for instance, in this color space. So whatever people are seeing as a feature, I can find a mathematical algorithm to program it. All right, now I've got an algorithm, and I can make a feature vector instead of one feature. Now I got 5 features. I can make a feature vector and train it, and then I can classify, is it level 1, 2, 3, 4, or 5. So that's what I did, and it was pretty successful, although in a small data set. So my second challenge, the wall that I hit, was data privacy. I had only 41 or 42 images like something to work on. And to get more data, I had a lot of challenges because hospital doesn't want to give data, and there are a lot of procedures for that. We have to write some papers about explain the project, why it's going to be used, where it's going to be used, is it going to be published or not. It goes to university, then it goes to hospital, then in hospital, if it passes the board after some months, patients can maybe sign something to accept it, and then the data comes, and it's a never-ending process like something. And that was really tricky wall, and we are engineers, we are waiting for data to work. We cannot wait 1 year to get data, and we were really getting frustrated. We need data to do more testing. And to get more data, we found a way to use GANs. And you heard about generative adversarial networks probably, which make those fake faces. All the faces you see here on the picture are fake faces, none of them are real. So if it's possible to make such realistic faces that even you, for instance, cannot understand it's not real, we can maybe make so nice fake skins to test. So that's what we did. If you're curious about GANs, generative adversarial networks, they are quite intensive networks because there are two networks competing with each other. One neural network is the generator that you see with the blue box there, and it's trying to make fake images. And one is the discriminator that you see with the red box. And that network is trying to learn how to differentiate between real examples, some few real examples, and the fake ones. So different discriminator is working like police. It's trying to stop the fake data. It's trying to become more successful to stop fake. And that strengthens the generator because generator is learning how to make better fake, which drills the discriminator finally. So we've got really nice fake data, more realistic fake data. So these are two computing neural networks all the time trained to get better and better what they are doing. And they generate really good or realistic images at the end. So I'm from the Netherlands, so that I'm use Dutch images here just to explain it. The generator tries to make fake data, and we've got only few real examples that you see on the top. And here the cat picture was not so real. It didn't pass the discriminator, but generator learns to make better fake. And at some point, discriminator cannot distinguish that it's fake. And this fake data drills the discriminator, and we've got a nice, good-looking fake data on our database. This is how we made so many images and had opportunity to test the algorithm. So we tested the new algorithm again with making fake data, giving it to unit to first get automated semantic segmentation, then extracting those 5 features and giving it to our classification network to say is it level 1, 2, 3, 4, or 5. And well, so far we've got successful results, but still it needs to be tested in larger people, I would say, to become like a real application. Now, okay, this was a pinch off from AI work that I've done lately, and I will go more details both in remote sensing and medical when you've got questions later at the end. I'm not pretty sure we've got maybe diverse audience or more researchers in the group, so I don't want to give so many lecture to you to not bore you. I want to render or discuss here some ideas. What is coming next? Okay, we've tried GANs, we've tried semantic segmentation, we've tried deep learning and all the things we extracted. Segments, we classified different things. So what is next, where it is going? when people ask this question, where it is going, what is the next thing, most of the people maybe answer, it is AGI. The next step is artificial general intelligence, of course, which knows everything better than AI. That will not be my answer to you. I don't find the AGI, first, I don't find it achievable, honestly. And secondly, I don't find it as a goal to achieve, because an AGI can be obtained if you've got really a lot of data. For instance, this Sophia robot is connected to internet and can Google, when you ask a question to Sophia robot, Sophia can Google things connected to internet and find the result and tell you the answer. It seems like she can answer anything, but if she's plugged out from internet, can she still answer anything? I'm not sure. If she sees a fire, is she going to escape? So is she going to give a response? Or if she sees something strange happening in front of her and not ask a question, is she going to react before you ask a question? For instance, somebody is having a heart attack in front of her. Is she going to get worried and call the hospital? She can call the hospital because she's internet connection. But if she's not trained to do that, she's not going to do that. She's not going to call the hospital if somebody is fainting in front of her. So I don't think that she will achieve AGI, and I don't see it as a goal to achieve, because when you've got a lot of data and when you've got everything connected, you can do anything anyway. And I don't see as an intelligence goal to achieve, honestly. I mean, maybe I'm offending some people who are working on AGI here. I'm not pretty sure. But this is not where I see future must go in the field of AI. Where I see as a future of AI, that at least I wish to see if it's really going to become more intelligent and more useful to everyone, all researchers, people who use it, and to environment also. I want to see those 6 things. One is self-awareness, sort of like being conscious by itself, but not literally consciousness, because consciousness has a lot of different definitions that open to discussion. I would like to see self-awareness, which I will describe a little bit later. I want to see AI using less data, like we did in our example. We didn't use thousands of patient images, we used 42 patient images. And also, I wish to see, for instance, without using GANs, making more fake data, maybe if it's still possible to learn things from less data. I will give you more examples soon. I want to see lifelong learning systems, really lifelong learning, like, for instance, a system which learns 30 years, 40 years, 60, 80 years, and to see that it's really becoming more conscious of making decisions. And I want to know that if it's really possible to add imagination to AI. I want to have AI which can be modeled without even training. We said less data, but maybe even without training. And I want to see AI without AI. So I will describe you one by one these 6 things. One is said self-awareness. This idea I got inspiration from Industry 4.0 that's upcoming. So what is expected from Industry 4.0? In Industry 4.0, the expectation from machines is that machines should be able to diagnose themselves. For instance, there's a machine in the factory, it's broken. The machine must know what is broken and even maybe suggesting how to fix it. So machine must be self-aware, and this is what's expected from Industry Revolution 4.0. And I expect the same thing from AI. For instance, if AI is not performing very well, a neural network, let's say, it's not giving good performance, it's given 70% performance. And when it's testing, I want AI to know that is it because maybe your training data was unbalanced. Maybe you didn't introduce a type of noise. Maybe your neural network should have more layers to be able to discriminate two different classes. So what is really the problem here? I want an AI to be able to tell it where the problem is coming from, to be self-aware, by considering how it was trained and also how the network is structured, to tell if it's the problem from training data or if it's a problem from the structure itself. Maybe I need a different architecture to be able to answer this problem better. To be self-aware, that's the first thing that I would expect us to be focusing is the next step in the AI. The second thing, needing less data. I mean, most of you probably have kids. I don't have one, but I would expect a kid. If I sit here with a kid, if I say, these left two things are stars, and these three things, even though they are different colors, at the right side are clouds. I got only 2 and 3 examples from 2 different classes. And this kid would be able to tell next time when I show something if it's a star or a cloud. I don't need to show 2,000 examples to kids to be able to discriminate stars and clouds groups from each other. How can he or she do that? So abstraction. The human brain is able to extract abstract features and to learn from very tiny little bits of data. Maybe here also our imagination works, because our imagination can also make more combinations of these stars and clouds in our minds by scaling up, down, and turning it around and things. But AI is not able to do that. So the second thing, how can I go to abstraction, and how can I learn from abstract features even if I've got 2 examples from one class? Can I train a neural network? Only with 2 data can I train a deep learning neural network, for instance. So that's something I believe we need to be looking at in order to make AI more intelligent. I don't think an AI would stay intelligent if I always need 2,000 examples to train something. That's going to be really boring and ridiculous at some point. And the third thing, I don't know if we can ever test or simulate this, because we cannot keep a computer on in infinite time. Is it possible to really learn better and better? And how can we, of course, validate how the performance is going, if it's possible to implement lifelong learning for real? Of course, we are looking at reinforcement learning a lot, but we've never tested it in infinite time, and we don't know we can ever do that. So that's something, an open question. I don't know the answer, but I wish to know is where the AI is going. I wish to know if it's possible to simulate or test lifelong learning. And fourth, we need to find out how imagination works in our mind, and how to add imagination to AI to make AI more intelligent. Imagination, in my opinion, is making simulation, but in forward time. So I'm training my brain but by just projecting the time to the future. So training has happened in the future. Let's say I'm walking in woods here, and I've seen this tree trunk laying on the ground. And when I see this tree trunk, even though I've never fallen down in woods earlier in my life, I never had an accident when I'm hiking. I had no falling experience. Um, when I see this, my brain imagines, if I go straight, if I cannot jump high enough, I would fall down. So I make a route planning in my mind. Can I turn all around it, or is it in a height which is possible for me to jump over it? And I make a route planning. But if you put a robot there to make a route planning, you really need to put it on gazebo rows, or I don't know, VREP or whatever simulation environment, and you need to crash the robot 2000 times to this tree in order to learn with reinforcement learning that finding the optimal route, maybe not on top of the tree, but turning around. You need to really have negative experience to train the revert function and to make a route planning, for instance, in AI. But in reality, in real life, as a human, I don't need to have bad experiences. I can imagine the bad experience and I can make the decision without the bad experience. So is it possible for AI to make forward simulation and to assume what would be the revert from this action and then making a decision without needing to crash 10,000 times? So this is what I understand from imagination. And I really suggest you to look at this paper, and there are also some other papers around becoming more popular these days. How to find the optimal architecture for a neural network, and how to find the optimal weights without even training. You don't have any training data, and you don't do any training, and you find the optimal weights by just using some probabilistic theory and make an estimation what could be the best weight combination to get a good classification result out of it. And this is quite impressive in my opinion to look, and in future maybe we get better at this. We can have a neural network which doesn't need to be trained, or we design it this way and apply transfer learning when we've got real data to achieve good performance so quickly. And the sixth, AI without AI, what I mean is here, we need to find AI, artificial intelligence, which are using algorithms that we are not maybe which are not available at the moment, maybe. So we need to develop more intelligent algorithms, but simpler. For instance, for designing something simple, 2 minus 1, what's it? Do I need to see 10,000 examples of what is 1, 5 minus 1, what is 3 minus 1, what is 4 minus 1? Maybe things that we are doing so simple way right now, they don't need deep neural network to do. Maybe we need to find algorithms which really do not need so many deep layers, because training so many deep layers really costs the environment a lot. And we are at the age of somewhere our environment is really breaking down on our head right now. We've got pandemics, we've got climate change, we've got all the scary events going on about food security, water security, and so many things. And now we are so much interested in training AI and training an AI model that maybe we are not even going to use it. We just want to publish a paper and we will not use the model anymore. Training this model costs 600 times more than making one flight CO2 emissions to our environment. So I'm an AI scientist. I love AI, but I've got honestly a love and hate relationship with what's going on in this field, because I'm not fond of really training things just for the sake of having something so deep. Maybe we can achieve some models, uh, smaller but intelligent or different ways. So that concludes my talk for now. Thank you very much for your attention. And in order to find more, if you visit my website with my first name surname.com, you will see a newsletter. You can subscribe there, and you will also find a link to my YouTube channel where I put my lectures. And if you want to be a guest on my YouTube channel, please send me an email. I will be honored. And you can also contact me on Twitter. I'm so much honored that you gave me this opportunity to access people, intelligent people who work in this field, interested in AI, using AI in real life. And I will discuss questions with you. Now we can switch the language to languages.
Okay, thank you so much for the presentation.